Cool. So today, proof in the pudding is going to be a bit different from what people are used to, if there's anybody who came before. It's called The Other Dark Forest, has kind of a vague title, and it's going to be more about a story, or not really a story, but kind of like patterns that I've noticed as I've been working in the ZK space. So I'm sort of going to go through a number of protocols, and I'm going to explain how they work to some degree, and I'm going to identify that pattern, and maybe at the end we can like brainstorm, or if there's any ideas that people want to throw at me or anything like that. So I guess I just learned that dark forest might not be a ZK stuff specifically, but I like to use dark forest for ZK and for hiding stuff. And when I came up with the title, I was thinking that there's a lot of stuff in the real world that's not on chain. And, you know, like you can think about Web 2 or, completely offline. And these are things that maybe we can use on chain or in ZK protocols to do cool privacy applications. And so also maybe I should say that today I'm going to focus on the privacy aspect of ZK, which is something that we tend to ignore. A lot of people use the compression aspect of ZK, but this time I'm going to talk about privacy and and what kind of cool things we've been able to do with it. And so just as a spoiler alert, we're going to talk about public keys, pub keys, and the sort of like these pub keys are in the wild and that we find and that we can use to do stuff with it. Okay, so the first protocol I'm going to talk about is called ZKLogin or zkJWT. There's always a ZK in front of it, so that's going to be easy. And this one, so actually, I was part of the audit of ZKLogin for SWI. Now I know how to say it correctly. And that's probably one of the first time where I saw a ZK application that was deployed and that was used. And I was actually, I thought it was really cool. I was like, wow, okay, that's one cool usage of ZK. In retrospect, makes a lot of sense. And so the whole idea of ZKLogin was like, imagine that you don't want people to handle accounts with keys, because the handling private keys is kind of complicated. And so we're looking at what else can they use to control their accounts. And we noticed that there's this whole world of SSO, single sign-on, where people already manage accounts with their email providers like Google or their Facebook accounts or Apple or etc. And so SSO is basically a bunch of implicit public keys. It's not like there's a registry of all the SSO stuff, but you can go to Google and you can look at their SDK and you can see that they have public keys in there. And so we have public keys here. I don't know, I'll rewrite it. Yeah, public keys. And what are they signing? These public keys are signing what we call JWTs, JSON Web Token. It doesn't matter too much what they look like, but basically the idea is to take these JWTs that, let's say Google signed for you. So Google signed the intent that you were trying to log into something with Google. They sign this JWT and there's a number of fields there. So it comes with a signature. I don't know, I'm going to call it Sigma. And there's a number of fields here that sort of authenticates the intent, who is doing what, and who you are. So you can imagine there's like at Gmail, something at gmail.com. There's the app. There's the app you're trying to log in. There's like a nonce thing, which is not too important, which is something to prevent replay attacks or the app ID is something so that you cannot take a signed JWT and just move it somewhere else. So you know that you're receiving this thing because the user intended to connect to you. It's a whole protocol. I don't want to talk too much about the details, but if you want to look at it, it's part of this OAuth protocol, specifically OIDC, OID Connect, OpenID Connect, which is like a small kind of extension of OAuth or like a kind of simplified OAuth just for SSO. And so they tell you how to sign this JWT. There's a standard. And that's basically what they use in this ZKLogin. They use that standard. The naive way to use that without ZK is that basically you used an app to control your wallets, you log in with the app, and using the nonce thing where you can put whatever you want, you put your intent, maybe you want to transact or you want to transfer some coins. You get a signature over that, you deploy it on chain, so you send that on chain, this is the blockchain. And there's a smart contract on the blockchain that verifies that jailability. It verifies the signature, it checks who is in the jailability, so it knows what accounts you're associated with, and then it checks what you want to do, and then it does whatever you want to do. But that kind of sucks, of course, because there's no privacy involved. You're deploying your email on the blockchain, and nobody wants to do that. So what you can do here is, you give it to a prover, I guess, and you create a proof, and then you submit the proof on the blockchain. And that's basically, it's a very simple protocol to explain. That's basically the idea behind ZKLogin, is that you're just verifying in a circuit that there is a jailability, so you have to do some parsing, this some JSON, right? That there is some email that's associated with some accounts, and we can talk more about that. And it comes from the right app, and maybe you expose the nonce if you want to say this is the transfer they want to make. Does that make sense before I go more into the, yeah? So there's a few things that are interesting to mention here. Maybe the first thing is the unlinkability of this protocol. So where can I write it? Maybe I'll use a different color. Let's write it here. It's a very dark red, unlinkability. And I had it here. So the unlinkability is interesting because here you want to use that proof to say this account is authorized to do that transfer, right? But you don't want to release the email. So you have this sort of like linkability problem where you want to associate that proof to the email in that proof to an account on chain. And so usually what people do here is that they derive some unique identifier. In some other contexts, you can think of them as nullifiers, if you've heard that term before. But here, we're not nullifying anything. We're just trying to create a unique identifier. And so you can think of doing like. Does that make sense? By the way, this issue. If it doesn't, interrupt me. But so the unique identifier, I don't know, UID. You can think of it as doing like a hash of the email here. But even that is not a great solution because you can just brute force. You can try different emails and see what identifier they give you. So usually they want to add some secret here. Maybe let me use some red. You want to use some garbage, some secrets that you always reuse when you derive that thing. And maybe you can control several accounts by changing that thing here. But the problem now is that we have a secret, and it's probably, random looking and long enough so that this unique identifier looks like hides the email address perfectly. And so the problem here is where do you store that secret? And so ZKLogin actually has a paper now. When I looked at it back then, it didn't have one, but no, they have a nice paper that explains to you what you can do with it, and basically either your application stores that for you. So there's kind of a trusted third party that can theoretically check if you exist or these kind of things, and they'll give you the secret, or you can sort of derive that from your password. And these kind of problems, we already know them for like many years of password hashing research, and so you can use it's kind of embarrassing because I forgot the name of the. People used to use PBKDF too, but we're supposed to use the new standard, which is not that new anymore. Does someone know someone knows the standard that won the password hashing competition like 5 years ago or maybe more? I forgot the name. It doesn't matter too much because everybody still uses PBKDF2. There was also some interesting work from Stanford. I forgot the name of that balloon hashing, I think it was called. But it doesn't matter too much. I just wanted to say that there is some issues here, and it's kind of tricky. And this unlinkability issue is always going to come back, or it's often going to come back in the protocols, these privacy protocols we're going to talk about. Does that make sense? Yeah?
Who's the attacker in the like reversing, like just brute forcing a hash and trying, I think
right.
You have to do it for a long, long time unless we know a subset of emails that are the possibilities. So like who's the...
Yeah, the attacker is like, and also the attack is kind of weak, right? It's just like, I want to see if that email has transacted in the past. Or it's not that weak actually. So you can, if you, for example, I want to attack you, right? I know you're using this thing. I'm going to try to figure out what's your UID so that I can see all your transaction on chains.
By hashing my emails that you know of.
Yeah, exactly, by hashing your email. Yeah. Does that make sense? The other thing that I can mention, because I thought that was interesting, if you look at the ZKLogin paper, they're like, this is kind of tough to create these proofs. That's going to be another theme that's going to come back. But instead of creating proofs every time, which kind of sucks, we can optimize this protocol by in the nonce not putting the intent, what you want to do, but putting a public key here. And so here you're sort of using that to authenticate a public key, an ephemeral public key. Ephemeral public key, it's a long word, I'm not going to write it. And then you can use that public key for as long as you hold it in storage. You can use it to sign transactions, and on-chain they will, or you can make it expire if you want. You can put whatever you want in that nonce, right? So you can say this will expire in like after 3 tries or after an hour, like whatever. So yeah, this is just optimization, but I wanted to mention it because it really sucks for clients to produce these proofs, and so maybe I'm going to write it down here as a client-side proving. Oop. And that's going to be the other theme, which is right now, it kind of sucks to create proofs. I mean, people are coming up with all these nice client-side proving schemes, so I'm not sure what's the state of the art, but basically, if you're in a constrained environment, which could be your browser, your phone, or your laptop for some laptops, it might be that creating a proof there's too much overhead, even though the circuits are pretty small. Actually, the circuits are not small. I will mention that, but I will need another color for that. I think I'm out of color. But essentially, it's kind of tough to create these proofs, and so you want to minimize that, and you want to make it as efficient as possible to create these proofs. Maybe I'll mention it now, but for a lot of these protocols, what you have is that you'll delegate the creation of proofs. So either you create schemes where you can sort of mask the private inputs, and you ask someone to create a proof, but they don't really see what's in the proof. Or people have been using TEs. So maybe let's write them down. So be clever will be the first one about delegating. And maybe, Kobe, you can tell me if I'm missing one at the end. Have a short, super small circuit. So if your circuit and the proof is pretty small, usually you're not going to have that much overhead. Or a cool proof system that's nice with client-side proving that has that in mind, so it doesn't use too much memory, etc. Or I've seen that a lot. Delegate to a TE. So this one is interesting because we had a previous sessions on TEs, so you can watch that. And the other one I'm thinking about is to do an MPC. So I'm going to call it zkSAS. zkSAS. Just because there's one paper that came out that called it zkSAS, and I like the name. But basically, you imagine an MPC, so multi-party computation. You have a service of many people, and you're distributing your witness. So you're distributing your you're sort of cutting your JWT, kind of like Shamir secret sharing style, and you give a piece to everybody, and together they create the proof, but they don't know, they only have like a part of the input to run that circuit.
And that's the same as collaborative snarks, right?
Right. So zkSAS is basically like a I don't know if it's really an upgrade. It was like a number of insights to like improve co-snarks, from what I understand. But I don't know if there's anything newer than that.
By the way, in what's deployed today, you say what approach do you use?
So in what's deployed, so I think the delegate to T is the one that people use. I don't think ZKLogin uses that though.
Oh, okay.
I think they're delegating, if I remember correctly, and I think they're being clever at some point, but I don't remember.
Okay.
But there might be like you might just trust like some third party to not, you trust them with your information, but you're happy that it doesn't go on chain. But yeah, don't quote me on that. Just look at what they're doing. I don't want them to be mad at me. Cool. So maybe I'll remove the delegation here. And maybe I want to, a lot of these things are gonna come back, I can wait. But I'll tell you now, because I'm on a roll. But the other thing is really why do we want super small circuits? It's really because we're verifying signatures. So here to verify a JWT, we're verifying a signature. And verifying a signature is heavy. Like we don't know how to do it efficiently, especially when these signatures are not snark friendly, as we call it. So I'll write signatures or real world, real world, I don't know how to write. Real world signatures are not snark friendly.
What does it mean for a signature to be snark friendly versus not?
So the short answer is that your circuit is gonna be because of your proof system, your circuit is gonna be in a field. So you're gonna use values that are from 0 to like some large number. And if it's a field, if you can create a signature scheme that works well in that field, it's gonna be great. So a lot of, Mina does that, for example. Like signatures of the system are using like a Schnorr signature algorithm, which uses the curve of the proof system of Mina so that it's efficient to verify. If you have a signature algorithm like RSA or ECDSA, which is most of what we're gonna find today, then you have to do what we call non-native arithmetic. We have to simulate some other, big integers basically, or some other field inside a field that's not made for it.
So to be clear, it needs to be constrained to a subset of the existing field of the actual circuit, or is it like a super subset thing, or is it sort of separate?
So repeat that.
Like is a friendly signature always going to be a subset of the field of the curve for the circuit, or is it not as simple as saying it's a superset subset relationship?
So when you say subfield, are you being technical, or are you saying like the subfield or?
Maybe being a little bit loose with that.
Okay, so basically, whatever is snark friendly is very specific to your proof system and to the field that you're gonna use. So you see people use Poseidon as hash function, or Schnorr signatures for snark friendly signatures or hash functions. But every proof system is going to instantiate it differently because they use different fields or different. That's the short answer. But yeah, in the real world, nobody cares about snark-friendly stuff, so we're stuck with ECDSA, with SHA-256, stuff like that. There's a lot of bitwise operations. You're doing a lot of XOR, shifts, and or whatever, and it sucks. So that's why the circuits are kind of blown up. Actually, this was one of the competition in Z Prize that we helped organize was to accelerate these kind of things.
In this one, they also use RSA as well?
For JWT, I believe they all use RSA.
Yeah.
Right. Because people are kind of stuck in the past. Yeah. So RSA is like big integers, right? It's like 2,000 bits, 4,000 bits sometimes.
Yeah.
Cool. All right. Shall we go to the next ZKML stuff? Any other question here? And yeah, I just wanted to mention also parsing is an issue, but I'll mention it again. Here we need to parse JSON. It's kind of annoying to do. It's not the biggest issue, but I thought I would mention it. All right, ZKML. So this one is another one where, like, when people found this thing, everybody was like, "Wow, it's so cool." And in retrospect, it makes a lot of sense. But I remember that there was a before ZKML and an after ZKML. So hindsight 2020. But once people found out about that, it was like everybody was like, "Oh yeah, it makes a lot of sense." So emails today, people are using a standard called DKIM. I forgot what it stands for. Decentralized Key Identity Management, maybe? No, someone knows? Yeah. Don't quote me on that. And basically, this standard, it's a bit loose. It's interesting. I mean, email has gone through many iterations. There's many email providers, email clients, and all these things. So everybody's sort of doing things differently. There's also a parsing issue that really comes up here. But now we have these big email providers like Gmail. I'm going to keep using Gmail as an example, that will sign your emails. And so they are, again, public keys. Yay. These public keys are even more implicit. They tell you that to find the public key of Google, for example, when you receive an email that was signed by Gmail, they'll tell you, look at this DNS entry. And there at this DNS entry, you'll find the public key that we're using. And obviously, if you know about DNS, you know that nothing is encrypted or authenticated. I guess there's DNSSEC. I don't know how many people use that, but it's kind of a sketchy way to place these public keys in the wild. But anyway, so today, public keys are being or emails are being signed. And so you can imagine that what matters is that when you're sending an email to someone, there's like a from field, to field, subject field. I think there's a body, if you want the terminology. You have this is how things work. You have \r/n, I think. And this is, what you're signing sort of looks like that. They have some headers, whatever. And what matters is that now you can look at something like that. You can send it on chain, these signatures. We'll put the signature here. Oop. And you can have a smart contract that will verify this signature, and that will look at what is in this field. They will see the same email here. They'll be, okay, this, David@gmail.com has already sent an email because it's Gmail's public key that has signed this message. And so what does David wants to tell us? Maybe David can tell us in the subject, or David can tell us in the body. And so here we have some parsing to do. Actually, the people behind ZKML, I think, have this marketplace of regexes, which seems very interesting. And in your circuits, because of course we're going to want to do that in a circuit for privacy, you can sort of find where you are. This is even simpler than JSON parsing, because you just have to look for this \r/n as separators. Find the field you're interested in and just look at what's in there. And you can put your intent in subject. You can say, this is the application I'm using, and this is the transfer I want to make. I went a bit fast here, but does that make sense? I mean, it's probably even simpler than JWT, because everybody has used that. Everybody has used emails, right? And here you sort of have the same issue of unlinkability. You want to make sure that this email is not, you're deriving something unique from it. The parsing issues I think, can be much more problematic there. Although it could be that your application is simple enough that you can put everything in the subject or something like that. And we also have the same issue of client-side proving, where it's annoying. We have to verify signatures. We need a DKIM registry on chain to know, what's the public key of Google, what's the public key of like whoever. Yeah. Sounds good. I think that's all I have to say about ZK email. All right, the next one.
Do you remember any real-world apps using ZK?
I think ZK P2P was using it. I heard they were doing, like if you receive an email from Venmo that you transferred them money or something like that, you could. And no, I've seen, we just audited one the other day. I guess I can't mention who's using it, but what I'll say is that there's a big blockchain that's using that for account recovery.
I was going to say, like, the big issue is basically if Venmo changes even like one section on their email, it all breaks, right?
Right. So for account recovery, it works well because that's your protocol.
Yeah.
For a Venmo or anything that relies on, and that's, by the way, that's the problem with zkTLS also. I mean, we can come back to that. But you're working with APIs that might change things. And these are not even API, right? They're like implicit APIs basically. Email can sort of change, but right now we're happy with the. There's so many different clients that things have to ossify, right? But yeah, good observation. All right, ZK Passport. I go to the next thing. So ZK Passport, I think the idea was floating for a while. Actually, I just listened to a podcast on the way here about that. Jan Myers was talking about it on the ZK podcast. And they did this paper called ZK Creds with Michael Rosenberg, ex-coworker of mine. Actually, my very first intern 10 years ago. ZK Creds. I don't know if that's true, but in the podcast, Jan Myers was saying that he believes that maybe they were the first one to like scan like a passport with the NFC chip in the passport and actually create a proof of that. So it's interesting. Apparently, they have a bunch of ideas on what to do with that. I haven't looked, but if people are interested. I don't think ZK email has a paper, but at least we have a paper for that, and we have a paper for ZKLogin, so that's great. The idea of ZK Passport is that this is even more implicit, right? There's no list of all the public keys of all the governments, right? So some people are gathering they're creating these registries of public keys, but there is no, it's kind of hard to find them. Public keys, but yeah, sort of. And essentially in your passport, there's a chip if you have a biometric passport, and I don't know, there's a symbol for the chip, I don't know how to do it. And if you scan it, basically you're reading something, and in that data that you're reading, it's almost like a magnetic band on a credit card. What you're reading is just some data and some signature from some passport entity. And it really looks like a PKI. There's actually, so like data, passport data, and it's signed by some intermediate CA, and that is signed by a root CA. So I've never heard about that, that's how public key infrastructure work. So here we have a 2-tier level. And they did something interesting. So we worked with Self at zkSecurity to audit what they were doing. And they were doing something interesting where they really wanted to improve client-side proving. So they not only delegate to TEs, but they also, if you want to create these proofs, they also separate. They also separate this signature verification from this signature verification, so that you don't have to do double signature verification inside the same proof. The data that is signed here is just a bunch of concatenated data. There's some parsing to do because they use that horrible encoding, ASN1 encoding, and it basically has your name, date of birth, nationality, stuff like that.
Can the like NFC chip produce like a fresh signature on like some challenge?
Like, great question, because that's what I want to come up with, the issue of unlinkability. The issue of unlinkability is even more annoying here because of what we call passive authentication. So whenever you're reading something that's dumbly like giving you the data, like a debit card or this kind of thing, we call that passive authentication. But in Passport, that's actually the name of the protocol. And here, the signature is not ephemeral, or there's no like, they cannot sign a challenge or anything like that. So if someone has seen your passport at the border and they, they keep a copy of what they scanned, or if someone like, I don't know, gets too close to you or something like that, I mean, that's always an issue though. If someone has had your passport in the past at some point in time, they can use it to do whatever your circuit is doing, right? So there's a new thing called active authentication. So this is very good naming from whoever created these standards. And basically, you can send a challenge, they'll sign it, and you know that the challenge could be the block header, like whatever, or the block height or whatever, and you know that since they could sign it, they're in possession of their passport. And I think Germany came up with another protocol to go even further, where they didn't want. I never really understood why, but there's another protocol, a third one, I forgot the name, and not every passport has it. And basically, it allows you to create these ephemeral public keys. You do a different key exchange, so that not only you can prove that you had the passport, but it doesn't really tell you. You cannot use that as a thing to prove to someone else that you were there when they verified you. I think that's what it does. So we'll call that 1, 2, and 3 German stuff. I don't know.
Like to make it completely non-transferable?
I think that was the reason. Non-transferable, yeah. I didn't look into that, so I can't tell you more about that. But 4, maybe I'll mention zkID. I don't know if that's a name that people have coined. I think there's a company called zkID. But maybe it's more interesting to call it zkID versus zk Passport, because there's a lot of regional IDs. So there's the European Union ID, there's the Indian ID, which is called Aadhaar. Wait, Aadhaar? Aadhaar. There's probably a lot more, and usually they use better, they use like active authentication. They tend to use active authentication. Yeah, I don't know if do you guys know if Aadhaar uses active authentication? Yeah, we have a yes.
Project on PSU, right? PSU did something on that.
Right. I know Self is working on that as well. So I think because of the unlinkability, and by the way, for the unlinkability, there's plenty of ways to solve it, which also has solutions in the world of password hashing. So you can use oblivious PRFs and plenty of things to try to get a unique identifier. That nobody can recreate or nobody can like brute force it. I'm not going to mention it. Maybe I'll write it down if people are interested. But OPRF is like one of the ways, or like a decentralized OPRF or these kind of things. What else can I say about that? I mean, that is super interesting as well. If you think of like doing KYC or like proving your age or proving that you're of some nationality, people have been using that to do airdrops, for example. When you think of like ID and ZK, probably a lot of people think about ZK Passport. So any question? Oh yeah.
So just curious about the architecture in the normal PKI architecture. If things get invalidated, so for example, intermediate certificate authorities change and sometimes they get hacked.
Yeah, it's kind of a mess, this PKI. Basically, some people, they all use different signature schemes and hash functions. So I know Self has like a very nice page where you can see all the countries and what algorithm they use. Some of them will have revocation lists.
Okay.
So you can check if like an intermediate CA has been revoked or something like that.
Then, like if I have a passport with passive authentication, then I have to like reissue the passport? Like,
Yeah. I mean, that's why they will ask you to reissue passports, right?
Okay.
Like sometimes you'll have to do it before, you have to do it every 10 years or something like So they're on a roll, but that's why they have a PKI, so that people have time to change passports. There's also issues there, like it's hard to identify someone uniquely. They can lose a passport, get a new passport, they can change their name. So there's always kind of a CBL. Is it CBL or CBL? CBL? I don't know how to say that word. But there's a CBL kind of issue there as well. But yeah, whenever you use identity, like there's always kind of a social, kind of a human aspect to it as well. So these are just tools, and it's interesting to see what people come up with using that. All right, so, okay, maybe I should ask you, what's the pattern here? Have you guys, I guess I was supposed to say it at some point, but do you guys see a pattern in all these applications? It's not a tricky question. It's really not. Yeah.
You got people signing things.
Yeah, pretty much. Where, it's like a lot of the time when people come up with ideas of like, oh, I came up with this super ID, I'm going to use ZK to do that. I'm always like, why don't you just use a signature? And so a lot of the time you can just replace the ZKP with a signature and your protocol works fine, right? But what's interesting is that doing the reverse, replacing a verification of a signature with a ZKP is actually very interesting. I've seen much more interesting protocols built around that idea. Yeah, so besides the issues on linkability, client-side proving parsing, what's the pattern here is that you can find very interesting applications by figuring out who is already signing stuff in the wild, where the public key is in the wild, and what can we do with it. Maybe I'll mention, I wanted to mention zkTLS. It's not really that. If you think of zkTLS, so if you don't know zkTLS, it's a protocol that allows you to prove that when you connect to a website that is authenticated with TLS, the response you get is something. And in TLS, when a client talks to a server, so you're the client, you talk to Google or something like that. By the way, we have a session on that. If you want to learn more, you can check the videos. The problem is that the server doesn't sign the response back. And so here we have the web PKI, we have certificate authorities and everything. They sign the certificates of websites, but you can't really prove any content response from that. And so zkTLS sort of came up with an idea, which is, let's just create that public key. Let's just come up with a new entity, and they call that the notary. So you have a notary, and this guy, or maybe multiple guys, will act as like stamp, approval stamp machines. And I don't want to talk too much about that because I already did a session on that. But basically, there's different ways of doing. But there's the MPC way and the proxy way. But it doesn't matter because in every case, you can see them as just like notaries that are stamping your ciphertext, and then you can prove or your plain text. Ciphertext, and then you can prove by decrypting them in a circuit that there's some content in your queries and in your responses. That's all I'll say about that, but I just thought it was interesting because it's like if you don't have these public keys, you can just still create them, and you still have that same pattern of verifying signatures and doing something else. Verifying signatures and then selectively disclosing something, I would say. That's the pattern. Maybe I'll write it here. Up. Verifying SIGs plus selective disclosure. Disclosure. Cool. I mentioned the use case of airdrop, but I mean, there's different use cases. You can control an account, you can do all these things. I thought another use case that was interesting was whistleblowing. You can always sort of, if you can prove that you're part of a set of public key and you sign your message with that, I guess, yeah, so you have a lot of applications where like for whistleblowing it becomes interesting. Or you could prove that if you have you control the signature of you can prove that you control the private key behind the public key of Satoshi and like sign a message with it, for example. I mean, here you could just sign a message with a. All right, that's a bad example. Just think of whistleblowing as it stands on its own. Okay, so I think that's sort of the end of my story. And at this point, I was like, maybe we can do a brainstorming. I think this is a good pattern to find interesting applications. And I was trying to think, okay, what else is there? What other public keys are there that we could be using in something like that for such a pattern? And I was thinking of like WebPKI, SMIME, I don't know how they say it. But anyway, do you guys have any ideas of public keys that we can find in the wild? And I would maybe have interesting ZK applications? Kobe, you mentioned GitHub public keys the other day. Commits are being signed. Maybe there's something we can prove there, which would be interesting. Come on, guys. You need to come up with the next big idea in ZK. I need you. And maybe we can also stop it here and we can come up with you don't have to do the brainstorm.
I guess you can, like, a lot of NFC chips have like unique keys and things associated with them. I guess that you can effectively take existing NFC chips or QR codes and effectively like attach some provenance to some ownership.
Yeah, I would say.
But like
Yeah.
that's kind of already a thing with like authentication. A lot of authentication protocols sort of do this.
I mean, it could be interesting. I'm not sure. I mean, there's a lot of in the hardware, or maybe I don't know if this ends up being like part of IoT, like the Internet of Things. But there's a lot of objects in the world that sign stuff. I heard cameras are like some cameras will sign pictures. All these TEs and stuff like that, they have their own PKI, like TDX has a PKI, SGX has a PKI, SIM cards, bunch of secure enclaves. Like, yeah, I'm not sure what's interesting there about that. But it's an area to discover. Yeah. All right, maybe let's stop it here, but if you get an idea, don't tell anyone and send me an email first with the idea. All right, let's do that. Cool. All right, thanks.